When you have a function capital F, it's called an antiderivative of lowercase f on an interval I if the derivative of capital F is equal to lowercase f. What does that mean? Like, what are we saying here? Well, what we're saying here is that we could have an original f of x, which you can see pictured here. And we can see that that original f of x is x squared. If I took the derivative of x squared, my answer would be 2x. So when I take the derivative, this is my derivative graph, which is a line. It's linear. So when you're given a quadratic function f of x that's in blue, your derivative is the red one, which is linear. So what we're saying is antiderivative, the concept of antiderivative, is that if I took an antiderivative, which they call an integral, and they use with this integral symbol. So integral or antiderivative is opposite of derivative. If I took the integral of 2x, my answer would then be x squared. So that's not, of course, the only answer, because even if I had that parabola started, instead of it being at 0, 0, even if I started that parabola here at 0, -1, the only difference between those two graphs would now be that this function, which I'll just call g of x, just have a different name. This g of x is x squared minus 1. And if you think about taking derivative of that g of x, I would get the same antiderivative of 2x. So when you're doing an antiderivative, you have to remember that the constant on the end of the function isn't taken into an account. So like the only difference between the two blue ones is that one of them is a constant of -1, which is down below the other one. But they make the same derivative. So therefore, when you go to take an antiderivative, there is more than one answer for the antiderivative, depending on where your original constant would be. So what does that mean? Let's see if we can be a little more specific. So what that means is, like, if you were looking for the antiderivatives of cosine of x, or the next one, again, they would show antiderivatives this way. They would say the antiderivative of cosine x. And they always put like a dx on the end, because remember when we're taking derivative, we say what we take derivative with respect to. Well, when we take an integral, or when we do an antiderivative, we should say what we're taking the antiderivative with respect to. So I'm taking the antiderivative of cosine x with respect to x. And I know that that answer must be sine x, because the derivative of sine x is cosine x. So antiderivatives and derivatives are opposites. In this next example, h of x, if I did the antiderivative of this binomial, I could do it in two parts. I could do the antiderivative of the 1 over x part and the antiderivative of 2e to the 2x. And if you think about derivatives backwards and you think to yourself, what derivative gives you 1 over x for an answer, you would probably remember that the answer is ln of x. In other words, the derivative of ln of x is 1 over x. As far as e to the 2x goes, the antiderivative of e to the 2x would be e to the 2x. And again, you're probably thinking, well, where did the 2 go, right? But think backwards. If you thought, what's the derivative of e to the 2x, you would have to remember that the chain rule is in place. So the derivative of e to the something is still e to the something, but then you have to multiply by the derivative of the exponent to use the chain rule. So antiderivatives, you have to think the chain rule backwards. Or, as we'll see in the next section, if you used a substitution technique, it would make your life a whole lot easier and you'd have to think less. At any case, so far we've got our antiderivative, except what if the original function had a constant on the end, like a 3 or a 4, and we took derivative of that constant? The derivative of any constant disappears and becomes 0. So when we're doing antiderivatives, we should always add a constant onto the end of our antiderivative to show that when we take derivative of a constant, it disappears. And people always use c as our constant. So again, in showing antiderivatives, we use our integral symbol. The SE-shaped thing is called an integral sign. The function that sits next to that integral sign, the thing that you're taking the antiderivative of, is the integrand. And we always put the dx on the end because that's the variable of integration. It tells people what you are integrating with respect to. So now you may take a second to pause the video and see if you can remember what derivatives would produce these things here that we're now taking the integrals of. In other words, as we said in the last slide, the integral of cosine of x is sine of x. Of course, we could also have a c, or a constant, that we've taken derivative of, and it would disappear. So, thinking backwards, the derivative of sine is cosine. The derivative of c is 0, and it disappears. Therefore, the antiderivative of cosine, or the integral of cosine, would be sine x plus c. Again, pause the video and see if you can remember all of these formulas backwards. Okay, so this one would be, of course, derivative of cosine is always negative sine. So going backwards, the derivative of sine is negative cosine. The derivative of tangent is secant squared. So the integral of secant squared is tangent. The derivative of negative cosecant is cosecant cotangent x. Again, they're opposite. The antiderivative to this one is secant. The antiderivative to this is negative cotangent. The antiderivative of e to the x is e to the x. As we saw in our last example, ln of x, taking derivative of that produces 1 over x. So the antiderivative of 1 over x is ln of x. This next one is infrequently used, but we know that this would be the derivative of log base a of x. Remember, the derivative of log base a of x is 1 over x times ln of a. So that's that going backwards. The antiderivative of a to the x ln of a is a to the x. And again, I'm remembering to put the constant on each and every one, because when I take derivative of any constant, it becomes 0 and drops out. The integral of 0 is still 0. And I think in this next example, this is meaning that this is an n minus 1, all on the same level. It looks a little bit funky. But if you think backwards, if you had x to the n, and you were taking derivative of that, we know the n would go to the front. So I think that this is also going to need an a here, because the derivative would be that the n would go to the front and get multiplied to the a, and then we would subtract 1 from the exponent. So again, anytime you want to check your work, just go ahead and take derivative of the antiderivative that you just got and see if you get the same thing that you started with, and you do. So again, every time you're trying to go to take integral, you know that you're going backwards, and you know that if you have something like this, which is a trinomial, you can just integrate each section. So again, think about how your derivatives work with polynomials. If I was taking derivative of, say, let's do the same one. Hopefully it doesn't confuse you any, but let's just do the same one. If we were going to do derivative instead of integral, I know that my exponent, well, first of all, my exponent would drop to the front, and then I would subtract 1 from the exponent. And the derivative of 2x would just become 2. And the derivative of 5 would become 0. So we're trying to go backwards. So in this case, we notice that the exponent went to the front first, and then we subtracted 1 from the exponent. So when we're going backwards and we're trying to integrate, we want to do it in the reverse order. So I'm going to go ahead and add 1 to the exponent, and then instead of multiplying, I'm going to divide by the new exponent. Let's do that again. There's a 2 in the front. I would add 1 to the exponent. I would divide by the new exponent. And in the case of 5, my x would have to make a return visit. Again, anytime that you're trying to, also, don't forget to put a plus c on the end, because we're integrating, and we could have had a constant. So again, think about like checking your work. And before I check my work, let's just go ahead and simplify this a little bit. So when I'm checking my work, what I would want to do is do derivative of that. So I'd be taking derivative of my x cubed over 3 minus x squared plus 5x plus c. So if I was checking this, the 3 would go to the front, and I would subtract 1 from the exponent. The 2 would go to the front, and I would subtract 1 from the exponent. The derivative of 5x is 5, and the derivative of c is 0. So I can see, indeed, I do get the same answer back. So my check proved that I did it correctly. Just like when you're taking derivatives, when you're doing integrals, fractions aren't entirely helpful, so I would probably want to, also radicals aren't really helpful. I would probably want to make this into a 1/2 exponent, and I would want to make this into a negative 1/2 exponent. And now I can go ahead and do the same rule I just did, which is that I want to add 1 to the exponent. So 1/2 plus 1 makes 3/2. And I want to divide by the new exponent. So if I divide by 3/2, it's the same thing as multiplying by 2/3. Likewise, I have a 2. I'm going to add 1 to the exponent, so negative 1/2 plus 1. And I'm going to divide by that exponent. So if I divide by 1/2, it is multiplying by 2. And don't forget to put a constant back. So my final answer here would be 1/3 x to the 3/2 plus 4x to the 1/2 plus c. Don't forget, you could always check your work by taking derivative and make sure you get the original answer back. You could pause the video and see if you can come up with the next answer. You would want to work on it the same way. They're talking about the general antiderivative. Antiderivative just means that we're going to integrate. So if I'm integrating 3x to the negative 1/2 plus sine of 2x with respect to x, I would add 1 to the exponent and divide by the new exponent. So if you divide by 1/2, it's the same thing as multiplying by 2. When you're going to integrate sine, I know that I come up with a negative cosine, so I probably want to make this a minus instead of a plus, because the derivative of sine is cosine, but the integral of sine is negative cosine. And now if I think back and I'm like, okay, if I go to take derivative, I would have to do derivative of negative cosine, which is sine, but then I would also need the chain rule, and I'd have to multiply by 2. So in this case, I'm going to divide by 2, because it's the opposite function. Again, if you're stuck, we will go over something called substitution, which makes this a little bit easier. But if I was doing this derivative, your derivative of cosine, you know, would be sine. And then you would multiply by the inside function derivative. So the derivative of 2x is 2. And I can see that that works because the 2's cancel. So I know that it works. And don't forget to put a plus c on the end because you are integrating. The only thing left to do would be to simplify this 3 times 2, and then you'd be all set. Okay, we're going to talk about something called an initial value problem. That's when you're asked to find an antiderivative, but you're not asked to find the general antiderivative, which means that you have all of these little c's on the end. The c's are general antiderivative because that constant could be anything. It could be 5, 10, I don't know what that constant is. When I take derivative of any constant, it becomes 0, drops out, so it doesn't matter what the constant is. But in this next example, they're saying they want the antiderivative, but they want it to go through the point 1, negative 1. So not just any antiderivative, but one that goes through a specific point. So what you're going to do in this case is you're going to first of all find the antiderivative. The antiderivative, again, you're going to add 1 to the exponent and then divide by the new exponent, which means my antiderivative is y equals x cubed plus 3. X cubed plus c. Now, that is called the general antiderivative. It is a collection of derivatives. C could be anything in this case. But what I want is I want this function to go through the point 1, negative 1, which means in this function, my y ought to be negative 1 and my x ought to be 1. So I can go ahead and substitute that point in for x and y. And then I find out that c would be equal to negative 2. That means that the specific antiderivative, the answer to the initial value problem, would be y equals x cubed minus 2, because that's what I just found c to be for this particular case. Okay, so in this example, they're starting off with giving you, and this came out of my math lab just to kind of expose you to the weirdness that my math lab sometimes does. So it's giving you three pieces. It's giving you this, which you know is the second derivative. It's giving you this, which is telling you how to evaluate the first derivative. And it's giving you this, which is giving you a point on the original function, r. So let's go ahead and start off with the second derivative. And what I'm going to do is, when they say solve the initial value problem, it means I want to get back to an original r of t. What is r of t equal to? So in order to get back there, I have a second derivative given, and I know that my first derivative would come from integrating my second derivative. So when I integrate this second derivative, I would get, adding 1 to the exponent, so negative 3 plus 1, and divide by that new exponent. And I know that there would be a constant involved. So my dr over dt would be negative t to the negative second plus c. The second little cloud I've put at the top there says that that first derivative, when you evaluate it at t equals 4, the answer would be 4. So what that means is I'm going to substitute t is 4 in, and my dr over dt will be equal to 4. So I'm going to just go and do my substitution. Dr over dt is 4. My t is, my t is 4. So I'm just replacing t as 4. And now I'm going to solve for c. So I have 4 equals negative 1 over 16 plus c. It means that 4 and 1/16 is c. That means that c is 65/16. So dr over dt is negative t to the negative second plus 65 over 16. So now I'm down to dr over dt, but I want to get back to r. So I know in order to get to r of t, I need to integrate my first derivative. So I'm going to add 1 to the exponent, which makes t to the negative first. And when I divide by that negative 1 exponent, I now have a positive. 65 over 16ths would have a t returning. And again, I have a constant c. This is now why they gave you r of 1 equals 2, because this is giving the point that t is 1 and r is 2. So I'm going to go ahead and substitute that now in. R is 2, t is 1. And that will allow me to find c again. So I have 2 equals 1 and 65/16. I know that's kind of weird, but that's when you add them together. And that would be 16 plus 65, that would be 81/16. And so I can say that this is 32/16. I'm subtracting 81/16 to get c. That means that c ends up to be negative 49/16. And that means that my original r of t must have been 1 t to the negative first plus 65/16 t minus 49/16. Hopefully I haven't made any weird fractional mistakes there. My guess is probably not, considering this problem came from your Pearson, my math lab. Sometimes the answers are weird. Okay, so other formulas to kind of flash back to other times. Don't forget you have your inverse trig functions. So if you're integrating something that looks like that, that would be inverse sines formula. If you're integrating something that looks like that, that would be inverse tangents formula. And this is your inverse secant formula. You may want to take a second to pause this video and try the next examples just to see if you can get the answers on your own.